Today we're going to review vectors, which is a topic that I hope you're already very familiar with, but in my experience, maybe we need a little bit more practice with vectors. We're going to be using vectors all semester. And things to keep in mind about vectors are vectors have three things that are very important to us. They're going to have a magnitude, they're going to have a direction, and they're going to have what's called a line of action. So a vector could be a force vector or a velocity vector or a position vector. So we're going to deal with a lot of force vectors. Let me draw a force vector for you. So if here is an x-axis and a y-axis, and I have a force vector, okay, it's going to have a magnitude. If it's a force vector, maybe the magnitude is 37 pounds. What we mean by the direction is it pointing straight up, straight to the right, down, or at what orientation? So we oftentimes give that information by an angle. Maybe the angle is measured from the x-axis or the y-axis. Giving you guys the magnitude, I've given you the direction. What in the world do I mean by a line of action? Well, the line of action is the line that force acts along. So you can imagine taking that force vector and just drawing a line that goes through it. We can take force vectors and we can slide them up and down along their line of action. And that line of action is just a line at the exact same orientation, same angle theta. And what it means is that it doesn't actually matter whether the force is applied at point O or at a point right here, or a point out here, or a point back there. The specific point of application is not important. What matters is the line that it acts through. So we can slide vectors along their line of action. We cannot move them in any other direction, though. So what line of action allows us to do is we can slide a vector along its line of action. We are going to need to sum force vectors in this class. We can do that a couple of different ways. If I have a force F1 in this direction, and I have a force F2 down in that direction, we can sum them using what's sometimes called the triangle rule or sometimes called the parallelogram rule. I actually like the parallelogram rule a little bit better. The idea is that you're just going to create a little parallelogram by drawing lines that are exactly parallel to your two vectors. So you see how I just created, I took that line and made a parallel to it, took this line and made a parallel to it. And the nice thing here is you don't have to think about actually moving either of your vectors to do this. We've created this little parallelogram, and the resultant vector is going to start where these two vectors start, and it's going to go all the way across and end at the other side of the parallelogram. We are going to call this F sub r, which means the resultant force vector. So our resultant force vector, we're going to use the resultant whenever we're adding up forces. Resultant force vector, well, that is equal to F1 plus F2. But they have to be summed in a vector fashion. We aren't just adding up the magnitudes. We also need to account for the fact that their directions are different from each other. So I like this parallelogram rule if you want to think about this graphically. Some people will instead create a triangle, either that triangle or that triangle. The same thing works with a triangle. You have to remember to put your vectors head to tail. And I don't like the idea of taking this vector and moving it up there, because I just said you can only slide a vector along its axis. So we could take this vector and slide it back up that way, put it right here and create a triangle. That would work. Now, if we want to do this graphically, we're usually going to identify one of these triangles and then use either the law of cosines or the law of sines to solve for what's missing in the triangle. Law of cosines tells us that a squared is equal to b squared plus c squared minus 2bc cosine of angle A, where you would need to have a triangle. Side lengths are A, B, and C, and then our angles are opposite. So this would be angle A, this would be angle B, and this would be angle C. Law of cosines works well when you know two sides and the angle between them. So if I know side B, side C, and angle A, law of cosines will give me the other side. Law of sines can then be used to find the missing angles. Law of sines says that side A over the sine of angle A is equal to side B over the sine of angle B is equal to side C over the sine of angle C. So you can use that to find whichever angles are missing after you've used the law of cosines. We can solve problems this way. For most cases though, rather than doing law of sines and law of cosines, we're going to end up wanting to use what are called vector components. Let's talk for a minute about vector components. That is the other way to solve these problems, which I happen to like a little bit better. So if I have a vector f1, I can break it up into components in any direction I want. Basically, what I'm doing is I'm breaking it up into two vectors, a vector in the x direction and a vector in the y direction, that when summed, give me the overall vector f1. So this side here would be called f1x. This side would be f1y, and I could then write my vector f1. You might have done it with a little arrow on the top. I tend to put a line underneath it to indicate that this is a vector being expressed in its Cartesian components. I will have f1x. And to indicate that it is pointed in the direction of the x-axis, I'm going to use an I with a hat on it. And then I will say that f1y is the component in the j direction. And what are these i's and j's? They're what are called unit vectors. I have a coordinate system where here's my x-axis and here's my y-axis. What they are is I is a little vector pointed in the direction of the x-axis whose length is 1. Remember how vectors have magnitudes and directions? Well, I is specifically the vector pointed in the direction of the x-axis whose length is exactly 1. And then j is the unit vector pointed in the direction of the y-axis. So what happens here is if I take f1x and I multiply it by this unit vector I, what I get is a vector in the x direction whose magnitude is f1x. Well, that's what I want. And then if I take f1y, that's this magnitude right here, and I multiply it by j, it means I'm taking and going in the direction of the y-axis exactly this far. The magnitude f1x, and I say go that far in the x direction, and then I say go this far in the y direction. If you do those two steps, you end up with the vector f1 that we wanted in the first place. Then we can do that for f2 as well. We would then write down our f2, which is pointed this way, and it's going to be made up of an f2x and an f2y, and then I can write this vector in Cartesian components using f2x in the I direction. And then since that f2y is pointed downward, I might call it minus f2y in the j direction. I would make sure there is a negative sign there indicating it's going down and not up. Then to get the resultant force, I would simply add them up. So you'd end up with f1x plus f2x in the I direction plus f1y is a minus f2y in the j direction. And now I have my resultant force without needing to remember law of sines or law of cosines. From there, I could find the magnitude and the direction using Pythagorean theorem to get the hypotenuse and an inverse tangent or something to get the angle. We'll do that with our example. So here's our example. We're going to solve it two ways. First, we're going to solve it using a triangle and law of sines and law of cosines. So let's read the problem. It says the resultant force, we want the magnitude to be 9 kilonewtons and we want it to be pointed straight to the right. So we're supposed to solve for t and figure out at what orientation it needs to act so that when you add it up with this 8 kilonewton force, the result is a 9 kilonewton force straight to the right. So let's draw a little sketch. I've got an x and a y axis. My 8 kilonewtons is directed down here. I want my final resultant force to be directed straight to the right. So let's draw it on here. And I want it to be 9 kilonewtons. And then I've got this other vector. I've got to add to the 8 kilonewtons. Basically, we're going to need to add to it right here. But if you want to draw it on your picture back here as our unknown t at an unknown angle theta, and then let's make our parallelogram. And we want the 9 kilonewtons to start where the tails are and end at the opposite side of the parallelogram. I want these two sides to be parallel and these two sides to be parallel. And so this side is our unknown missing t, right? This is t that we're trying to solve for, and then there's also the theta that we're trying to solve for. We do know one of our angles. We're given that this angle is 45 degrees. So this is great. I actually have a triangle right here that I know a side angle side, so I can use law of cosines. Law of cosines says that that missing side, t squared, is going to equal the sides that I know, 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of the angle between them. Solving for t, we get that t is 6.57 kilonewtons. I rounded that to 3 sig figs. And now what I need to figure out are all of these other angles. We know this one is 45 and that's opposite the side T. Why don't we find this one over here? I like the idea of this one because then this angle is equal to that angle. So if I find this one, I just have to subtract it from 90. Call it alpha, and then let's use law of sines to find that angle. Law of sines says that 6.57 kilonewtons over the sine of 45 has got to equal 8 kilonewtons over the sine of alpha. So solving, we get alpha. And alpha comes out to be 59.4 degrees. Okay, that's not the angle we wanted. They wanted theta. So reminder is that guy right there is theta. It's the orientation of t relative to the y-axis. So I can solve for that by saying theta plus alpha is 90 degrees. So theta is 30.6 degrees. So it's an example of a problem that is actually really fast to solve with law of cosines and law of sines. However, the step that will stymie a good number of students in trying to do this is figuring out which of these angles and how are they related to theta. So if you struggle at all with figuring out, remembering all of your geometry rules about parallel lines and alternate interior angles, I recommend going straight to Cartesian components. So let's solve this problem using Cartesian components. So to do that, I need to get all of my vectors into Cartesian components. So we'll say F1 is that 8 kilonewton force. So it's got a magnitude of 8 kilonewtons. And then to get the x component, I would need to multiply by cosine of 45 degrees with the I. And to get the y component, I would multiply by sine of 45 degrees with a j. And I just realized I put the wrong sign in there. It's downward, right? You guys remember sines and cosines? Here's my triangle. There's my 45. SOHCAHTOA tells me that sine is the side that's opposite the 45 and cosine is the side that is adjacent. So I take 8 kilonewtons times cosine 45, I'm getting that side, and 8 kilonewtons times sine 45, I'm getting this side, which is pointing downward. Let's do F2. That's the one I'm trying to solve for. Oh, I have no idea either of its components or its angle. I'm just going to call it F2x in the I direction plus F2y in the j direction. If you want to call it tx and ty, you can. And then finally, the resultant. Oh, I know the resultant force. It is 9 kilonewtons in the I direction, 0 in the j. How are the resultant related to F1 and F2? Fr is equal to F1 plus F2. So we can sum the x components and the y components separately if we want. So if I do just the i's or the x's, I end up getting 8 kilonewtons cosine 45 plus F2x has got to equal 9 kilonewtons. Solving, you get F2x is equal to 3.3431 kilonewtons. That's not a final answer, so I don't want to round it to 3 sig figs yet. I want to keep all my decimal places. So next, the j component, I'm going to end up with minus 8 kilonewtons sine of 45 plus F2y is equal to 0. So F2y has got to be equal to 5.657 kilonewtons. We're almost done. Now we want to get magnitude and direction. So for magnitude, what I've got is F2x right here, F2y right there, and I need to find, I'm going to use Pythagorean theorem. And if I want to get my total F2, I need to take the square root of F2x squared. That's 3.3431 squared plus 5.657 squared. And when you do that, you get 6.57 kilonewtons. Now I'll round to 3 sig figs because I'm done. And then what about theta? We wanted to find theta from the y-axis. That is this angle right here. So that theta is also equal to this theta by using alternate interior angles. So what I end up getting is that the tangent of theta is the side opposite theta. Opposite side is the x side, and the adjacent side is the y side. So opposite is the F2x, which is 3.3431, and the adjacent is the 5.657 side. You solve and you get theta is 30.6 degrees. And as far as I'm concerned, you can solve it either way. You get the same answer. They're both correct. So do what is easier for you. I will say if they're both easy for you, focus on Cartesian components because we're going to be using them all semester long. Let's do another example. Here's one where we are definitely going to use Cartesian components because I've got more than 2 vectors. And I can only use the triangle or parallelogram rule to add 2 vectors at a time. And I want to do this all in one step. So what I want to do is take those 3 vectors and break them up into their Cartesian components. So that's my first step. Get all vectors into their Cartesian components. Let's do F1. It has a magnitude of 850 newtons, and then I need to find the horizontal component and the vertical component. Well, there's a shortcut here. If I had this angle theta, I would use the cosine of theta to get the X side and the sine of theta to get the Y. Well, I can do that with a shortcut. Let me show you what the answer is going to be. For the X component, I'm going to end up with 4/5 I, and for the Y component, I'm going to end up with 3/5 J with a minus sign because it's pointed downward. So here is a cool shortcut that I want you to use all semester, because our textbook loves to give us these little 3, 4, 5 triangles instead of the actual angle. So here's the shortcut. The force is along a line with a slope of minus 3/4. Okay, here's a picture of that. Picture shows 3, 4, 5 triangle. So you can go and find that angle theta if you want. You don't need to though. Here's where the shortcut comes in. We don't need theta. We need sine of theta and cosine theta. Well, wait, do you remember what sine of theta and cosine of theta are if you have a triangle? The sine of theta is the opposite over the hypotenuse, 3/5. See how that's 3 is opposite and the 5 is hypotenuse? And the cosine of theta is adjacent over hypotenuse, 4/5. If you want, you could first use an inverse trig function to solve for theta and then take the sine and cosine, or you can recognize that, wait, you already have a similar triangle where you know all the sides, so you can get sine of theta and cosine theta, skipping the step of actually solving for theta. I know a few of you really mix up sine and cosine a lot. So here's a hack. Whichever side is lined up with the x-axis goes with the x-axis. So it's just the side in that direction divided by the hypotenuse. So 4/5 gives you your x component. And then the y side, 3 over the hypotenuse, gives you your y component. So shortcut to find F1 in Cartesian components. The other two do not have a shortcut. F2 is pointed down and to the left with that 30-degree angle. So for F2, the magnitude is going to be 625 newtons. And then the direction to get the x component is opposite. If this is a triangle, it's the side opposite the 30-degree angle. So we'll use sine of 30, and it's pointed to the left. There's your x component. And then the y component is the other one. It's the adjacent side, and it's also pointed down. So minus cosine 30 degrees J. Finally, let's do F3. It has a magnitude of 750 newtons. It's up and to the left with a 45-degree angle right here. I am going to make sure I use cosine and sine correctly for that 45 degrees, even though sine and cosine of 45 are the same. We end up with a 750 newtons out in front. And then to get the x direction, the x side is opposite the 45-degree angle. That's that side of the triangle. So I'm going to use sine minus sine of 45 degrees in the I, and then it will be plus the other one, cosine of 45 degrees J. And it's negative for the x because it's going left, it's positive for y because we're going up. So that's our first step. We got all of our vectors, 1, 2, and 3 into Cartesian components. Next step is to find the resultant. Sum the x and y components. The resultant x force is going to be the 850 newtons times 4/5 minus the 625 newtons times the sine of 30 minus the 750 newtons times the sine of 45. If you multiply that all out and add it, you end up with minus 162.83 newtons. Now let's do the y component. Well, we're going to have first the downward 850 times 3/5. You put in a negative sign, 850 newtons times 3/5. Then for the 625, it's also a minus 625 newtons cosine of 30 and plus 750 newtons cosine of 45 degrees. That all comes out to be minus 520.94 newtons. Keeping extra decimals because those are intermediate calculations. Next, let's find the magnitude of the resultant force. The magnitude of the resultant, some books would write it like that with like bars on either side to indicate magnitude. Well, Pythagorean theorem is rx squared plus ry squared. And that's going to be square root of minus 162.83 squared plus minus 520.94 squared, which comes out to be 546 newtons. That one I rounded to 3 sig figs because it's my final answer for the magnitude. And what about the direction? I find this very helpful to draw a little picture. We have a negative x. So we're going left 162 as well as down 520. So our resultant force vector is right there. So when we go to find an angle, we need to be very clear about where that angle is referenced to. If I use an inverse trig function, I'm going to probably find that little angle alpha. The tangent of alpha would be the opposite side. That's my y component, 520.94, divided by my adjacent, which is the 162.83 side, right? I got my 163 and my 521 are right there. So do that inverse trig function, you solve for alpha, comes out to be 72.6 degrees. So if you wanted to give it measured counterclockwise from the positive x-axis, which is usually what the textbook is looking for, that's this theta. The theta is going to be 180 plus that 72.6. So it is 253 degrees counterclockwise from the positive x-axis. And we solve for theta and we solve for the magnitude.